So coordination compounds, we talked about coordination compounds a little bit, right, when we talked about acids and bases. So transition metals tend to form complex ions. I'm sorry, we didn't talk about coordination compounds, we talked about complex ions. So we have the central metal ion, and then we have ligands that are bound to it. And those ligands are Lewis bases. And what's the characteristic of a Lewis base?
Electron pair?
Yeah.
Donor?
It's an electron pair donor, right? So here, this is ammonia. Ammonia has a lone pair on the nitrogen. So that can come in here and donate that to one of the empty orbitals that cobalt has and form a covalent bond. So this is not, oppositely charged ions with ionic bonds. This is a covalently bonded ion. There was something else, but I forgot what it was. So the coordination compound is your complex ion with the counter ions, because you can't have a beaker of positive ions. You can't have a beaker of just negative ions, right? It's not going to happen. They'll react in a way to quit being like that. So, if you have a positive 3 charge here, then somehow you need something that's going to make up the difference. It could be 3 chloride ions, it could be 1 nitride ion, it really doesn't matter. These counter ions, they're important. It's important to know that they are there, but the reason we use net ionic equations a lot is because exactly what they are doesn't matter. They don't participate in the reactions, and we're not actually interested in them, so we just leave them out, right? So a coordination compound, a neutral compound consisting of a complex ion and 1 or more counter ions. So there's 2 types of interactions for that central metal ion. Primary valence is the oxidation state on the central metal. So cobalt 3+. 3+ is its primary valence. And then we have the secondary valence, also known as a coordination number, and that's the number of ligands, molecules or ions, that are bonded directly to the metal. So when these types of compounds were first discovered, this one was written like this in the form of a hydrate, where you've got cobalt 3 ion and the 3 chloride counter ions, and then there's 6 ammonia molecules incorporated into the crystal structure. Now it's written this way to more clearly reflect that the ammonia molecules are ligands on the cobalt, and the chloride is just there to balance the charge. So what's the primary valence on that complex ion? 3+. And what's the secondary valence? 6. It's the number of ligands. There's a lot of variations possible. We could also have a compound where a cobalt has 5 ammonia ligands and 1 chloride ligand, or 4 ammonia ligands and 2 chloride ligands. And so, yeah, fun times. So the chloride can replace the ammonia, it can act as a counter ion or as a ligand. And there is a question on the take-home exam where you need to think about this. Yes?
So if you were trying to make a particular one, how would you go about ensuring that you have the right number of ligands? You don't.
I have no idea.
Because each one of them would have their own kind of properties.
Yeah, they would. They're going to have their own kind of properties. Yeah,
Okay.
that's inorganic chemistry. Yeah. I didn't care for that one either.
Would
Could-
NAPS have a, oh, sorry,
Go ahead.
another counter ion? Because it's still like the same charge.
No, it doesn't, because this isn't a chlorine atom, it's a chloride ion. And so this mitigates some of the charge here. And so this ion here, the complex ion, only has a +1 charge. And this one has a +2 charge. Could ammonia be a counter ion?
Isn't it neutral?
It's neutral. It can't be a counter ion. So ammonia in this, set of combinations can only be a ligand. The anions could be a ligand, or they could be a counter ion. So that's a clue. So these complex ions are Lewis acid-base adducts. An acid and base coming together. The bonds form when the ligand donates a pair of electrons. So here we see an ammonia molecule acting as a Lewis base. It has a pair of electrons here that it can donate to silver. And there's two of these, and another one can donate to silver, and it will form this complex ion. Because these ligands are neutral, this complex ion has the same charge as the original metal ion. So if you're trying to identify what could be a ligand, it has to have a lone pair. And that's one of the reasons chloride can be a ligand, is the chloride ion actually has 4 lone pairs, right? Because when you gain that 1 electron, you complete the octet, and you've got 4 lone pairs. Any questions? So these are some common ligands and their names. Water, ammonia, chloride, carbon monoxide, cyanide, thiocyanate, oxalate, ethylene diamine, and ethylene diamine tetraacetate. And there's a reason it's abbreviated EDTA, because that's kind of a mouthful. And ethylene diamine is abbreviated EN. So this is the ethylene. Eth means 2 carbons. So we got the carbon here, and then there's a an amine group over here and an amine group over here, diamine. And this one, you have that same thing in the middle, but now instead of hydrogens on the nitrogens, you have acetate ions. Yeah. And what's really cool about this guy, it's got 4 places that it can really act as a Lewis base. It's these oxygens out here, and we'll see it can actually wrap around an ion and form 4 coordinate covalent bonds with the same ion. Yeah, rock star. So a monodentate ligand donates 1 pair of electrons. Bidentate, 2 pairs of electrons. Polydentate, 3 or more, right? So ox. There we go. Oxalate, often abbreviated OX, and ethylene diamine can form 2 coordinate covalent bonds. Donate 2 pairs of electrons. This is the Lewis structure for ethylene diamine, and we see the lone pairs here on the nitrogens. The polydentate ligands can donate more than 2. So 3 or more. And each pair of electrons is coming from a different atom. You don't have one atom making multiple coordinate covalent bonds. So here's EDTA. It's actually can be up to hexadentate. So we've got these guys on these oxygens. Those will form coordinate covalent bonds. And it's also possible for the nitrogens to do that as well. Usually we see 4, but it could be 6. So this is a cobalt-3 ion with 3 ethylene diamine ligands. And so this is one. We got the 2 nitrogens, and here's another one, and here's the third one. And here is cobalt with EDTA. Where is the cobalt? There it is. And so we've got the 4 oxygens. Wait a minute. Here's 1, 2, 3. It's using 3 of the oxygens and 2 of the nitrogens. No, I think this one's under there as well. I think it's using all of them. So there's another word for bidentate or polydentate ligands. It's called a chelate, or a chelating agent. So a chelate is a complex ion that has one of these things in it. It's a chelating agent. And these have a lot of uses. One of the things that happens in our qual scheme that we had for our lab practical, one of the first things we did was we added, what did we add? Not sodium hydroxide. We added ammonium hydroxide, right? If you added sodium hydroxide, most of the ions would precipitate out. But adding ammonium hydroxide, the cobalt forms a complex ion with the ammonia, and so it stays in solution. But aluminum can't do that. Iron can't do that. So we can use a chelating agent to kind of take an ion out of the picture because it keeps it from interacting with other things. So the coordination numbers that we see vary from 2 up to 12. 4 and 6 are the most common. The coordination number of 2 is only going to happen with the +1 ions. And in that first row of transition metals, because those guys are smaller, you're only going to have up to 6. The geometry is going to depend on the coordination number, but also the number of d electrons, because you can end up with d electron lone pairs. And so this goes back to VSEPR theory. So here, coordination number of 2 on opposite sides, that's linear. 4 can be either square planar or tetrahedral. And then 6 will get us octahedral. You can have an odd number, but thankfully we're not going to look at that. Naming coordination compounds. So there's a set of rules, and these were proposed by the guy who discovered coordination compounds. So some of the regular ionic compound naming conventions still hold. You name the cation first, and then the anion. The cation might be the complex ion. The anion could be the complex ion. Doesn't matter. Cation still goes first. So how do we name the ligands? So H2O is water, but that's called aqua. NH3 is ammonia, but that's called amine. And CO is carbonyl. Anything else is just the name of the molecule. But these guys are special. If you have anionic ligands, then you take the name of the ion and you modify the ending, kind of like we did for acids. If it ends in "ide," like nitride or chloride, then you get rid of the "ide" and that becomes O. So this is a chloride ion as a ligand. In the name, it's chloro. Something that's "ate," like sulfate, becomes sulfato. So we're just taking the E off and adding an O. And if it's an "ite," it becomes ito, sulfito. And, it's a good thing we didn't keep the D there because sulfito and sulfito, that'd be confusing. So we list the names of the ligands in alphabetical order. So this has some things in common with organic nomenclature. So you're going to name the ligands before the name of the cation, and they're going to go in alphabetical order. Because, you have to have some rule, right? How do you pick what order they're going to be in? So if we had ammonia and chloride and nitrite, so amine is going to be before chloro and before nitrito. And the one thing you have to watch out for there is aqua for water starts with an A, not a W. We're going to use a prefix to indicate how many of the ligands, only if there's more than one. If there's just one, we just put the name of the ligand in there. If there's more than one, we use di, tri, tetra, penta, or hexa. What if you have a ligand whose name has a prefix in it? Then you put parentheses around the ligand, and you use bis, tris, or tetrakis, which is another set of number prefixes. The prefixes don't affect the alphabetical order. Alphabetical order goes on the name of the ligand itself. So get that in order first, and then put the prefixes in there. So after you've done all of that, then you name the metal. So if we have a cation, then it's just like a regular metal ion. So these are all ones that form more than one ion. They all need Roman numerals, and so we include the Roman numeral in the name. If you have a complex ion that is an anion, we're going to drop the ending of the metal name and add 8, kind of to indicate that this is an anion. So we can end up with cobaltate. We're still using the Roman numeral, though, to indicate the primary valence of the metal ion. So if we look at this one, so here the metal ion is platinum, but its name goes last. So we look at the ligands first, and here we have amine and chloro. So amine comes first, and there's 2 of them. So this is diamine, and there's 4 of those, tetrachloro, and because this is an anion, it's not platinum, it's platinate, 2. diamine tetrachloroplatinate 2. And if you read ingredients lists, especially on junk food that have lots of chemicals in them, a lot of these names are just a series of prefixes and suffixes and element names, right? And so you can actually impress your friends by just reading through it. Diamine tetrachloroplatinate 2. Right? This one over here, again, this is amine, but there's 6 of them. So that's hexaamine, cobalt, this is positive, cobalt 3. You have to consider, like on this one, platinum does not have a 2- charge. There are 4 chloride ions, right? Overall, it has a -2 charge because the platinum has a +2 charge. So it's a lot of things you've seen before, but different, right? So your book lists these out for you. Oops. So here's some of the anion ligands and their names in the complex ions. Chloride becomes chloro. Hydroxide becomes hydroxo. Take the "ide" and replace it with "o." Neutral molecules. These are the 3 exceptions. The name of the molecule is water, but the name in the ion is aqua. And we have amine and carbonyl. And then this guy, ethylene-diamine, its name is the same. Over here is where we see what those metals would be named if they were in an anion. Because in the cation, they're just the same, and we don't need a list for that. So some of these are kind of fun. A lot of times they'll revert to their Latin names. So instead of sylvate or silverate, it's argentate, because silver is argentum. And that's where manganate comes from. And another one we've seen is chromate. So we had a metal in one of those polyatomic ions, right? Any questions? So here's the short version. Oh, I'm sorry. This is the other way around, writing the formula. So in the name, the cation comes at the end of the complex ion name. In the formula, it comes first. In the formula, neutral molecules come first and then anions. If you have more than one kind of neutral molecule or more than one kind of anion, then you go to alphabetical order. But you go neutral and then negative. So the metal's positive, and then you go neutral ligands, and then you go negative ligands. The alphabetical order there is based on the chemical symbol, not on the name. Aren't you glad we're not having a regular exam on this? Okay, name the following compounds. Well, let's identify what the ligands are. So, CO is called what? Carbonyl. And NH3 is amine, 2 M's, not to be confused with amine with 1 M. So who goes first in the list? Amine. So we're gonna go amine, and how many of those are there? There's 5, so that's pentamine, and again, things are a little sketchy about whether you keep that vowel at the end or not. So pentamine, and then carbonyl, and this is all run together, no spaces. Carbonyl doesn't need a prefix because there's only one. And then the name of the metal, manganese. And what is the charge on the manganese ion? I'm sorry, the manganese ion.
2 plus.
It would be +2 because both of these are neutral, right? There's one of these ions with sulfate, which has a -2 charge. So the +2 charge comes from the manganese, and so we're going to indicate that with Roman numeral 2, and then the name of the anion, sulfate. Pentaamine carbonyl manganese 2 sulfate. How about this one? So what's the ligand here? Chloride is the ligand, right? So the complex ion is in brackets. You can see why you put the brackets in there, because it could get confusing, right? If you wrote this without brackets, you're like, well, is the sulfate one of the ligands, or what's going on? So this is the complex ion here, platinum with 4 chlorines. But in the name, the cation goes first. So sodium. Chloride becomes chloro, and how many? 4. So tetrachloro, chloro. Platinate, not platinum, because that would be a cation. Platinate. And what is the primary valence of that?
2.
+2. Because so the sodiums here are a total of +2, and so this whole thing has to be -2. These guys give us -4, and so the platinum has to be +2. Sodium tetrachloroplatinate 2. Any questions? Mm-hmm. Yes, they're separate words. So there's still a cation and an anion, right? And the cation name is first, and then there's a space, and then there's the anion name. But even though the anion name or the cation name may have a gazillion letters in it, it's all one word. Yes?
Do the inorganic chemists love tongue twisters?
Probably. I didn't hang out with them.
Fair enough.
Yeah. And it was a really long time ago. Any other questions? Yeah.
Why does the chloride ligand have the -4 that you wrote by it?
Let's put that back. Okay. So why is this -4? Because each of the chlorides is -1. And so there's 4 of them. So there's a total of -4 charge there. And overall, this is -2 charge. So then the platinum has to be +2.
Thank you.
Yeah. That's just a matter of figuring out what the charge is. Sometimes it's not obvious. And, it's dumb to learn all this other fancy stuff and then get the primary valence on your metal ion wrong because you did it in your head, right?